Welcome! In this video, I'd like to show some examples of infinite sequences and series. An infinite sequence is an infinite ordered list of numbers, denoted as U sub n. Each U sub n is called a term. There are mainly four types of sequences in arithmetic: arithmetic sequence, geometric sequence, harmonic sequence, and Fibonacci sequence. I'd like to show some examples. We'll begin with geometric sequence. Its form is as shown. The general term is AR to the quantity n-1. Each term can be found by multiplying the previous term by a constant, which is called the common ratio. Let's take a look at an example. Here we can see the initial term as 10. We divide the next term by this first term 10 to find out the common ratio. 40 divided by 10 gives us 4. Just in case, let's divide the next term by the current term and get the common ratio as 4. So we can formulate this geometric sequence as 10 times the common ratio is 4 to the quantity n-1. Since we have the general formula for any term, we can find the sixth term by substituting 6 into n to get 10,240. Let's find out what Fibonacci sequence is next. The Fibonacci sequence is a series of numbers where the next number in the sequence is found by adding up the two numbers before it. Both f1 and f2 are shown as 1. For f3, this can be found by adding the two numbers before it, 1 plus 1. The f of 4 is found by adding the two numbers before it, 1 plus 2. The f of 5 is 2 plus 3. The f of 6 is 3 plus 5 to get 8. And so on. Here's a surprise. When we take any two successive, following in order, Fibonacci numbers, such as 3 divided by 2 to get 1.5, or 8 divided by 5 to get 1.6, or 21 divided by 13 to get 1.615. Their ratio is close to phi, which is approximately 1.618. This phi is called golden ratio. Please explore if you are curious about the golden ratio. An infinite series is the sum of the terms of infinite sequence of numbers. If we let S sub n be the sum of the first n terms, then these are called partial sums. Let's consider the given infinite series and some partial sums. The first example is shown. The first partial sum, S sub 1, is just the first term, so it is 1. The partial sum of the first two terms, S sub 2, is 1 plus a quarter to get 1.25. S sub 3 is adding the previous S sub 2 and the third term 1 over 16 to get 1.3125. In the same way, we get S sub 4 equal 1.328125 and S sub 5 equal to 1.33203125, and so on. It appears that if we add more and more terms, the sum is approaching some single value, 1 1/3, we can find out more on this value later. Let's consider another infinite series and their partial sums. The first partial sum, s sub 1, is just the first term, so it is 1. The partial sum of the first two terms, s sub 2, is 1 plus negative 1.5 to get negative 0.5. S sub 3 is adding the previous s sub 2, negative 0.5, and the third term, 2.25, to get 1.75. In the same way, we get s sub 4 equal to negative 1.625 and s sub 5 equal to 3.4375, and so on. It appears that if we add more and more terms, the sum is not going to be a single value. Let's find out this question again later. Let's go back to the previous two examples. The partial sums results are shown. For A, the partial sum was approaching a single value. If the sum of the infinite series denoted as S is defined, then we say the series converges. On the other hand, we can see the sum of the example B is not approaching a single value, or the sum is plus or minus infinity case. In another word, the sum S is not defined case. Then we say the series diverges. Let's find out the convergence of a geometric series. The geometric series is given by the formula as shown. Since we have seen the geometric sequence already, the series becomes the sum of each sequence. Just in case, let's recap the notations. The lowercase of n indicate the nth term, a is the first term, and r is the common ratio. Here are the rules for convergence and divergence for a geometric series. If the absolute value of ratio is less than 1, then the series converges to the value by the formula shown. However, if the absolute value of ratio is greater than or equal to 1, then the series diverges. Therefore, the sum of the series is not defined. Let's bring back the example A again to determine if the series is a geometric, and we can find the sum of the series. The initial term A should be 1. Next, let's find out the common ratio R value. To find R, we can divide any term by the preceding term, 1/4 divided by 1, or 1/16 divided by quarter. We can see the common multiplier 1/4. So R is quarter, or 0.25. And this is indeed the geometric series with a common ratio of quarter. Let's examine if the series converges or not. If we take the absolute value of R, which is the absolute value of quarter, then it is less than 1. Therefore, the series converges based on the criterion. Since it is convergent, we can now find the sum of the series by the formula shown. Simply substitute each letter with each numerical value to get 1 all over 3/4, which becomes 4/3, or approximately 1.3333, ... repeating decimal. We predicted this value before. Similarly, we bring back the previous example B question and see if this is a geometric series and convergence. First, determine the A value, which is the first term. So A is 1 in this case. Next, let's find out the common ratio R value. To find R, we can divide any term by the preceding term, negative 1.5 over 1, or 2.25 over negative 1.5. So R is negative 1.5. This is also the geometric series. Next, let's examine if the series converges or not. If we take the absolute value of R, which is the absolute value of negative 1.5, then it is greater than 1. Therefore, the series diverges based on the criteria. Since it is divergent, we cannot calculate the sum of the series. This time, let's take a look at a different type of question. We try to convert a repeating decimal to a fraction. Of course, you can convert it using a different approach. However, we'd like to apply the infinite series concept here. We write the repeating decimal 0.6565 as a fraction. First, splitting into the series form gives 0.65 plus 0.0065 plus 0.000065 plus and so on. The first term should be 0.65. Next, let's find out the ratio value. To find R, we can divide any term by the preceding term, 0.0065 over 0.65, or 0.000065 over 0.0065. Both give the ratio as 0.01. This is also the geometric series. We can see the common multiplier 0.01. So R is 0.01 or 1 over 100. And this is indeed the geometric series with a common ratio of 0.01. Let's examine if the series converges or not. If we take the absolute value of R, which is the absolute value of 0.01, then it is less than 1. Therefore, the series converges based on the criteria. Since it is convergent, we now find the sum of the series by the formula shown. Simply substitute each letter with each numerical value to get 65 over 100 all over 99 over 100. Cancel the denominator 100 from top and bottom to get 65 over 99. We cannot reduce this fraction anymore. So the given repeating decimal can be written 65 over 99 as a fraction. I hope you are comfortable with this topic. If you are curious, please explore about the series. Thank you for watching. See you again.